They say in most of the United States there's 4 seasons. There's spring, summer, fall, and winter. But I can tell you right now that in North Carolina there's actually 5. There's spring, summer, fall, winter, and hell's front porch. And that's exactly where we are here today on the 22nd of July. We're in hell's front porch here, standing in front of some corn. And we're going to talk about how corn responds to temperature here. I'm Dr. Ron Heiniger. I'm the cropping system specialist at NC State University. And we're going to look at this corn and how it's responding to this hell's front porch season here in North Carolina. You know, we often talk about water as a limiting factor in corn production, but really water is just a moderator for temperature, and that's really what drives the corn system. Temperature drives corn as far as its development, the rate and speed in which it develops ears and silks. It also drives the metabolic process of the plant. Here on this chart here, I show a little bit of the temperature response for corn here, and as you might see, or you're going to see on this video here, those limits typically define where corn performs the best. For instance, you got these survival limits here. Corn can take up to 110 degrees. Now that's not atmospheric temperature. Okay, let's be clear about that. That's the temperature at the corn leaf. And that corn leaf temperature is really moderated by, so when it runs out of water, all this radiant energy could drive that tissue above 110. So that survival limit, you're going to see some tissue that's burned here today that went above 110. Then we got growth range limits. These are limits in which the corn basically stops developing, and that's 95 degrees here. So yesterday it was up above 95 atmospheric, so you can imagine corn didn't do very much yesterday. The other temperatures here are optimal ranges here. For the purpose of today, why we won't talk a lot about them, other than to note that one of the optimal ranges here is 77 degrees at night. And that is pretty critical for us, because at night, that's when corn takes all that photosynthate and converts it into starches and puts it into those kernels in the ear. So if that temperature is above the optimal range, a lot of energy is wasted trying to keep the plant cool rather than making starches and putting them into the ear. So you can see here that we've got some different ranges here to define corn growth. Now, what can we do? You know, you and I, when it gets to be hell's front porch, we go inside to the air conditioner. We get a cool drink and we sit down and we relax there. You look at these plants here in this field here, they ain't got that choice. They got to sit here and take it. So how in the world are they surviving under these kind of conditions? Well, they survive by water. They transpire water through the plant. And as I already mentioned, whenever water becomes limiting, which it's very easy to do on bright, clear, sunny days in the middle of summer, we get these hot, dry spells, why then these corn temperatures go up. This chart here basically shows some of the canopy temperatures we're recording last year, and we're recording them again this year. We're doing that by using these little bitty sensors. Let me dig this out of my pocket here. These little bitty sensors, we attach them to the leaf, and then we measure how hot does that leaf temperature actually get. And you can see here, I got a little zone here where it's been above 95 last year. We're going to show you some of the data here in this video from what we've seen this past week this year. So indeed, we can easily get temperatures above 95 at that canopy. What can we do to help that corn plant survive in these kind of conditions? Well, we're trying some things here, and that's what this research plot is really all about, is looking at some different approaches. Some of them are familiar to you, such as managing row spacing and plant population. Now, how does row spacing and plant population help keep that plant cool? Well, it comes down to how much water that plant has available to it. So as you might guess, as we reduce our plant populations, each plant has a little more water, and we're not as many mouths at the trough, if you will. Or if we change our row spacing, so we move those plants apart from each other, you know, this is a day of social distancing, that's a new term here. Well, these plants are social distancing, and they're trying to give each of them a little bit better access to water. So again, we can look at some of that information that we've gotten last year when we looked at, there's row spacing here. The 20-inch row in this blue was much cooler than the 36-inch row here. We'll look at some of these plants here today and see how they're performing. And again, I'll show you some data from what we've seen this past week on some of this year. The other thing that, like I said, we could do is just reduce our population. And we've got that in this plot. We've got everything from 26 again to 44,000, just like we had a year ago. And again, here's information from a year ago where that 26,000 was much cooler than the 44,000, particularly at some critical times during the season, such as a week like this, where we have these excessively hot temperatures. So those are two methods that we can think about to try to moderate these temperatures here, give this plant a little better chance of survival. Again, we'll look at how that works. The other techniques that we're trying this year that are new is we're looking at things that might enhance the root development, might enhance how those roots reach out and find water. And we're doing that and measuring the results of that by using some sensors here. One of the sensors that we're using is a soil probe, and that probe is allowing us to look at how those roots are growing. And again, I'll show you some slides here in this video of what that looks like, how these roots are growing deeper each week, and that also gives us an idea how they're extracting water. So we've got some new probes in that we're measuring these soil properties, soil moisture, soil temperature, every 15 minutes through the day, recording that and sending it via wireless to a base station where we can read that data. So we're getting some idea how those are working. So the treatments we're looking at to try to determine if they're having an impact is we're using a product that's called a mycorrhiza. Endomycorrhiza, what really allows the roots to reach out better. They're fungi that actually invade the root tissue and act as root hairs in a way, reaching out into the soil. So we've made an endomycorrhiza treatment remarkably, or maybe somewhat funny. It's named Heat Shield. We'll see if it acts as a heat shield here this year. But it's an endomycorrhiza that we apply to the seed at planting time that then infects the roots and helps build those mycorrhizal networks. The other treatment we're looking at is one that has been around, but we haven't thought about it as a heat treatment, and that is a fungicide. Strobilurin fungicides improve the efficiency of the leaf to move or operate the stomata. So as a result, they allow that plant, when it gets hot, to shut down that stomata quicker, limiting water loss, and when it cools down, those stomata open up quicker, getting more CO2 into that leaf to make photosynthate. So we're using a fungicide treatment applied at 2 different times, V7 and again at VT, as a way of seeing if that improved leaf efficiency imparts a better heat tolerance and water conservation to this crop. Let's look at some of these treatments here and see in the field by direct observation how they're performing here as this crop tries to tolerate this heat on Hell's front porch here. This is what I would consider, based on our last year's data that we looked at, one of the better treatments here. This is the 20-inch row. Here we got this heat shield stuff that this endomycorrhiza that I mentioned here. So this should be our best. We got these plants spaced out. We only got 26,000 of them. We got the heat shield. So this should be everything we can think of to try to keep these plants cool. So let's take a look at it. Take a look at the plants themselves here, particularly as you know, at this stage, what's happening is that water is used up. These plants are trying to keep themselves healthy, so they're translocating it up the plant. So you're looking at the bottom leaves. How many are fired up? How much brown leaf area we have? That brown leaf area, of course, indicates that those leaves went over 110 degrees. So when that water left those leaves, they burned right up. So you can see here, most of this plot looks decent. I mean, it's not the best plot I've ever had, but it's greener and looks like it's tolerating this heat. You can see here these ears that we've pulled here. Again, not the best looking ears I've ever pulled from a cornfield here. We had a lot of rainfall early, so as you might guess, some stress there. They're decent ears. We'll have some corn here. The other thing I might point out while we're just standing here, here's our tower transmitting that soil probe data that we just mentioned a little while ago. So we got a probe in this plot measuring how these roots are growing and what we're looking at. All right, now let's move down. So this is nice because this is in order in this case. So now we got 32, so same as 20-inch, same heat shield, but now we've increased our population here. And again, now compare how many of these leaves you're seeing that are brown and the color of that corn there. It's starting to get a little paler. You're seeing more of these brown leaves at the bottom. And you can see, so these ears again, not too bad, but they are tipped. We're seeing less pollination to the tips here. Move down again here. We're now at 38,000, so we moved up to our next population level. Again, now you're seeing some brown leaf all the way almost to the ear. There's some leaves that have been affected by drought here in this crop. And again, a lot of tipping on these ears. In fact, there's one ear right here that's hardly got good pollination at all. So again, an indication of that heat stress that's in here. And then we'll look at the final one here. Here's 44,000 plants out there. Now I'm seeing some leaves in this canopy, even above the ear, that have some browning. So again, you're seeing this burning effect of this temperature in this 20-inch row here. Now let's compare what we saw with the better treatment, the narrower rows, the different population with heat shields, with a wider row. Again, I've still got heat shield here. We're not starting with the lowest population, but you can at least see some real differences here as row spacing starts to affect how these plants are crowded together and competing for water. So again, we're looking now, of course you can see a much wider row. Look how many of these leaves up by the ear are showing that brown effect. The ears don't look too bad. We didn't do too bad, and that's one of the things we're looking at, why sometimes even in a wide row we do still get better pollination than you might think. So there's 32,000. Let's move down here to this one. There's the one at 26,000. You can see a little more green here, but still the row effect is dominating. Moving those plants apart really helps them find more water, that social distancing like we just mentioned there. And then we go on here. Here's the 38,000 here. Again, lots of brown leaves down in this canopy here. And then finally, we'll look at this 44,000 situation here. And as you get across there, it's almost brown all the way up to the top, and you can see how pale this corn looks here. So, and again, the ears are severely tipped in this treatment here. So you see visually the impact of row spacing, plant population, and again, we're evaluating these different treatments here to see if we can moderate that temperature. When you're in hell's front porch, you gotta do everything you can that make that plant survive these types of seasons. And this is some of the things that you guys can do that'll help improve your yields and give you a chance to survive some difficult conditions.